Hello, welcome to a new lesson to study the Legendre Polynomials. In this case, we want to introduce the concept of the Fourier-Legendre Series. So, I should point out that we have made a lesson where we showed that if we have an infinite set of orthogonal functions, let's say, for example, a set of functions phi sub 1 of x, phi sub 2 of x, okay, and well, yeah, this is an infinite set. We showed that if this set is orthogonal, then we can write a function f of x as an infinite linear combination of these functions, okay. So we were worried about finding the coefficients of this linear combination. Perfect. So actually, we have another video where we show that Legendre polynomials form an orthonormal set. Okay, so that means that we are able to express a function f of x as a linear combination of Legendre polynomials, right? Remember that we use the letter p to refer to Legendre polynomials. Okay, so in this case, we are going to be interested in finding these coefficients. Okay, but in that same lesson where we showed this, we gave a formula to find the coefficients c sub n. Okay, so we got to the result that the coefficients of the infinite sum is equal to the inner product between f of x and the orthogonal function that corresponds to the n coefficient, right? Recall that we have the same index here and here. So this is like the inner product, but remember that we defined the inner product on a given interval, right? From a to b, okay? And then this is divided by the norm of the orthogonal function that we are using, that is this phi sub n of x over here. So what is the norm? Remember that in the context of vectors, we know that the norm of a vector b can be seen as a b dot b. Well, this is actually the norm squared, right? And if we consider the dot product between vectors as the inner product between functions, right, like a similar tool, we can say that the magnitude of a function f of x squared is equal to, well, the inner product of f of x squared, well, yeah, the inner product of f of x with itself, right, integrated on the variable x. Okay, perfect. So in this case, what will that be? Well, that is the integral from a to b of phi sub n of x squared dx, and I forgot dx here. Okay, perfect. So that is the formula that we are going to use to find the coefficients on the Fourier-Legendre series. So what is this going to be? Well, we can assume that f of x is going to be the sum from n equals 1 to infinity of c sub n, p sub n of x. And on the previous lesson, we showed that Legendre polynomials are orthogonal, and that means that, for example, if we take, let's say, the inner product of p sub n of x and p sub m of x, yeah, this is the integral from a to b of p sub n of x, p sub m of x dx, and recall that the interval of definition of the Legendre polynomials and its orthogonality property is going to be from -1 to 1, okay? That's important. So we showed that this is equal to 2 divided by 2m plus 1 times a Kronecker delta and m. So this means that if we are taking two different Legendre polynomials, of different order, this is going to be equal to 0, right, due to this Kronecker delta. Recall that the Kronecker delta and m is defined to be 0 if n is different from m, and 1 if n is equal to m. Okay, So this is like a quick way to define the orthogonality property for Legendre polynomials. Okay, so if we consider the case where n is equal to m, we are going to have the inner product of p sub n of x and p sub n of x that we just mentioned, that this is equivalent to have the norm of p sub n of x squared. And this is going to be the integral from -1 to 1 of p sub n of x squared dx. And if we use this formula, of course, this is just going to be 2 divided by 2n plus 1. So recall that this is the magnitude of the n-order Legendre polynomial squared, and that is what we need to use into this formula, okay? Just to be able to find these coefficients. And then we see here that we need to take the inner product between f and the n-order Legendre polynomial. So that means that c sub n is going to be the integral from -1 to 1 of f of x p sub n of x dx divided by, well, the norm of this Legendre polynomial squared, so that is 2 divided by 2n plus 1. So this can be seen as 2n plus 1 divided by 2, and then the integral from -1 to 1 of f of x p sub n of x dx. Okay, so if we want to construct the complete definition of f of x in terms of Legendre polynomials, we need to substitute this value for the c sub n constants. So that is going to give us f of x equals the sum from n equals 0 up to infinity, and then c sub n, but that is going to be 2n plus 1 divided by 2, and then the integral from -1 to 1 of f of x p sub n of x dx. And recall that this whole thing multiplies the n-order Legendre polynomial. So just for not to get confused, we are going to move this, right? Because this can be seen maybe as the element inside the integral. So let me bring it back to this position, just for not to get confused. So yeah, I think this will be the complete definition of f of x in terms of an infinite series that is actually a linear combination of Legendre polynomials. So we are going to make a quick example to see how can we express a function, very easy function actually, as Fourier-Legendre series. So that function that we are going to use is going to be the function f of x equals 0 on the interval -1 to 0, and then 1 on the interval 0 to 1. Okay, so just to make a quick graph of this, it will be -1 here, 1 here, and then we have a 0 here, and then let's say that this is the value 1. Okay, so that is the easy function that we want to express as a Fourier-Legendre series. Okay, perfect. So if we use the formula that we just found, well, we will have that f of x equals the sum from n equals 0 to infinity of, well, it is a 2n plus 1 divided by 2 p sub n of x, the integral from -1 to 1 of f of x p sub n of x dx. Okay, and we are going to develop just the first 4 elements to get the next. Well, if n is equal to 0, this will be 1/2 p sub 0 of x, the integral from -1 to 1 f of x p sub 0 of x dx, and then plus, what are we going to get? It will be 3 divided by 2 p sub 1 of x, the integral from -1 to 1 f of x p sub 1 of x dx, plus 5 divided by 2 p sub 2 of x, the integral from -1 to 1 of f of x p sub 2 of x dx, and then plus, it will be 7 divided by 2 p sub 3 of x, the integral from -1 to 1 of f of x, p sub 3 of x dx, and then so on and so forth. So we are going to be interested in calculating those 4 elements only. Okay, so we need to calculate p sub 0 of x, p sub 1 of x, p sub 2 of x, and p sub 3 of x. So to do that, I think we are going to use, well, the definition, right, for the Legendre polynomials. So that definition is the next. We have that the n-order Legendre polynomial is equal to 1 divided by 2 to the n factorial, and then the n derivative with respect to x of x squared minus 1 to the n. Okay, so if we want to calculate the n equals 0 element, we will get that p sub 0 of x is equal to 1 divided by 2 to the 0, 0 factorial, and then the 0th derivative of x squared minus 1 to the n. But the 0 derivative, well, is just the regular function, right, without taking any derivative. So that will be equivalent to have x squared minus 1 to the 0 power, which is 1. So that means that all this is going to be equal to 1. Okay, so that is p sub 0 of x. Then I should calculate a p sub 1 of x, which is going to be 1 divided by 2 to the 1 power, 1 factorial, the first derivative with respect to x of x squared minus 1. So what is this going to be? It is 1/2 and then 2x. So it is x, right? P sub 1 of x. Okay, perfect. So this is the n equals 1 element. Then we are going to take the n equals 2 as p sub 2 of x equals to 1 divided by 2 to the 2, 2 factorial, it will be, well, yeah, the second derivative with respect to x of x squared minus 1 to the second power, right? Remember that there is an n here at the exponent. So what is this going to be? Well, the first part is easy. It will be 1 divided by 8. And then I think the easiest way to do this is to raise this to the second power first and then take the second derivative. So this will be the second derivative with respect to x of x to the 4th minus 2x squared plus 1, which is going to be 1 divided by 8. And then what happens if we take 2 derivatives? Well, it will be 4x to the 3rd power and then 12x squared and then minus 4. Okay, yeah, I think that's it. So if we simplify a little bit, it will be 3 divided by 2, x squared minus 1/2. Okay, so that is p sub 2 of x. Perfect, so we are going with the last one. It will be p sub 3 of x. So this is going to be 1 divided by 2 to the 3rd power, 3 factorial, and then the third derivative with respect to x of x squared minus 1 to the 3rd power. Okay. Yep, so this is going to be 1 divided by 8 and then times 6. Okay, so here we are going to raise this to the 3rd power. So if we remember the rule, we will have the first element to the 3rd power is going to be x to the 6th power, and then minus 3 times the first one raised to the 2nd power, which is going to be x to the 4th, and then times the second element, but that is just 1. Okay, and then plus 3 times, well, the second element raised to the 2nd power, which is 1 squared, times the first element, and then minus 1 to the 3rd power, right? So yeah, and well, yeah, we need to take the derivative with respect to x 3 times. Okay, so I think this is going to be 1 divided by 48, and then, well, let's take the first derivative. So that is going to be, well, the derivative with respect to x 2 times of 6x to the 5th power minus 12x to the 3rd power and then plus 6x like this. Then this will be 1 divided by 48, the derivative with respect to x, of 30 x to the fourth power minus 36 x squared plus 6, and then this is going to be 1 divided by 48, and then 120 x to the third power minus 72x like this. Okay, so if we simplify a little bit, we will get that this is 5 divided by 2 x to the third power minus 3 divided by 2x. Okay, I think that with this we are able to calculate the 4 first elements of the Fourier-Legendre series. Okay, so let me bring back this whole thing. Okay, so I just rewrote the formula that we just found and the 4 results for the Legendre polynomials. So we will get that f of x is equal to 1/2 p sub 0 of x, which is 1, and then the integral from -1 to 1 of f of x. But recall that from -1 to 0, f of x is equal to 0, and from 0 to 1, f of x is equal to 1. So that means that we can split this interval from 0 to 1, right? Because from -1 to 0, it's going to be equal to 0. So we are just going to take into account the integral from 0 to 1. Perfect, and f of x has a value of 1, and p sub 0 of x is equal to 1, and we integrate with respect to x. Then we will have plus 3 over 2 p sub 1, which is x, and then the integral from -1 to 1 of f of x, which is 1, times x, p, which is p sub 1 of x, and then dx. And then we will have plus 5 divided by 2 p sub 2 of x, which is 3 divided by 2 x squared minus 1/2. And then the integral, and remember that here is again the integral from 0 to 1. So we have the integral from 0 to 1 of p sub 2 of x, which is 3 divided by 2 x squared minus 1/2 dx, and then plus 7 divided by 2, all this stuff, 5 divided by 2 x to the third power minus 3 divided by 2x, the integral from 0 to 1 of all this thing again, 5 divided by 2 x cubed minus 3 divided by 2 x and dx. Okay, so those are the first 4 elements of f of x as a linear combination of Legendre polynomials. So what is this going to be? Well, we will have that f of x is equal to, I think this integral is immediate. Of course, it is equal to 1. So the first element is going to be 1/2. And then we will have plus 3 divided by 2x. And then what are we going to get here? It will be x squared divided by 2, evaluated at 1. It will be 1 divided by 2. Yep. And then plus 5 divided by 2. And we are going to rewrite this maybe for simplicity as a p sub 2 of x, right? So this 5 over 2 multiplies p sub 2 of x, and then what are we going to get here? It will be 3 divided by 2 x to the third power divided by 3 minus 1 divided by 2 from 0 to 1. Okay, and then we will have plus 7 divided by 2. It will be p sub 3 of x, and then this is going to multiply 5 divided by 2 x to the fourth power divided by 4 minus 3 divided by 2 x to the second power divided by 2 from 0 to 1. Okay, looking at p0 is equal to 1, we can say that this element is multiplying p sub 0 of x, and that p sub 1 of x is equal to x. We can say that this is p sub 1 of x. So we are going to rewrite f of x in terms of those Legendre polynomials. So f of x is equal to 1/2 p sub 0 of x plus 3 divided by 2 p sub 1 of x, and then it will be plus 5 divided by 2 p sub 2 of x, and then this is going to multiply. We can cancel these 3's. 1 divided by 2 minus 1 divided by 2, right? Yep, so these elements are going to cancel, and this is going to be equal to 0. Okay, and then plus 7 divided by 2 p sub 3 of x, that is going to multiply 5 divided by 2, 1 divided by 4, minus 3 divided by 2, 1 divided by 2. Okay, and then so on and so forth. So f of x is going to be 1/2 of p0 of x plus 3/2 p sub 1 of x, and then plus 7 divided by 2 p sub 3 of x times 5 divided by 8 minus 3 divided by 4, and all these things that we have here can be seen as 5 minus 6 divided by 8, which is equal to minus 1 divided by 8, and this whole thing multiplies 7 divided by 2. So at the end, this element is going to be minus 7 divided by 16. So just to rewrite the result in a more elegant way, f of x is equal to 1/2 p sub 0 of x plus 3 divided by 2 p sub 1 of x minus 7 divided by 16 p sub 3 of x, and then we keep going. So what we can say about this result is that, of course, and these three elements that we have here can be seen as an approximation of f of x on the interval minus 1 to 1, just like another way to approximate a function f of x. Okay, but remember that it is only on the interval minus 1 to 1. Okay, so this will be like the first three elements of the Fourier-Legendre series for the particular f of x that we gave at the beginning of the example. Okay, so I think that will be the final result of the lesson, just to exemplify how to find the Fourier-Legendre series for an arbitrary function f of x. I hope you enjoyed this lesson, and thank you so much for watching.